Okay, we're going to work on 7.4, number 29. If the function f from G to H is an injective homomorphism of groups and A is an element of G, prove that the order of f of A is equal to the order of A. Okay, so we're going to work down here. Right, I have a group homomorphism F from a group G to a group H. I've got A in G, okay? Now, what I need to do is I need to prove something about the order of this. So I'll say let this be, be such that the order of A, say, equals K in the positive integers. Okay. We could also consider the fact that we could consider the possibility that the order is infinity, but we'll focus in on this for now. Okay, so what I want to show that the order of f of A equals K. So what does this mean? So this means that we know A to the K equals the identity in G, and K is the smallest such positive integer. Okay. Now, in these order arguments, you're always going to use this smallest piece. So look for us to use that. Now, what do I need to show? I want to show something about the order of this. So I want to say f of A to the K. Well, so here's the thing. If you have f of A to the K, that's just f of A times f of A times f of A, K many times. Well, since this is a homomorphism, this uses the fact that it's a homomorphism, right? If you have f of A times f of A, that's f of A squared. So I actually have f of A to the K. Well, what's A to the K? Well, you remember back up here that the order is K, so A to the K equals E. So this is f of E. We know that a homomorphism maps the identity to the identity. Technically, this is the identity in G. This is the identity in H, right? So I have shown that f of A to the K is equal to the identity. Now I need to show that K is the smallest such positive power. Well, here's how you do that. You say, if there were J bigger than 0 but less than K, such that f of A to the J equals the identity, well, what then could we do? Remember, we haven't used that this is an injective homomorphism yet. So what do we know about this? Well, we know that this right here gives us f of A to the J equals E. Well, what else? We're trying to use injective. We know that f of E equals E. Well, if it's injective and A to the J equals maps to E and E maps to E, that means by injectivity A to the J equals E, contradicting minimality of K. Right? We said K was the smallest. J can't be smaller than it and still do the same thing. Therefore, the order of f of A equals K, which is the order of A. Dun 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 dun.